So I'm doing my presentation on quantum tunneling. Quantum tunneling is where a subatomic particle will appear on the other side of a potential energy barrier, even though it doesn't have enough energy to cross it. For example, if you look at the ball here, in quantum tunneling, if the ball was to roll down the hill, it would somehow appear on the other side, even though it doesn't have enough energy to cross over the big one. This diagram here shows an electron wave hitting a barrier and crossing it, again not having enough energy to do so. Again, if you look at the example of the ball, in classical physics, if the ball was dropped from here, it would only ever reach here and it would roll back down and end up somewhere here. However, in quantum physics, the ball would somehow go over this hill and end up on the other side. It was first discussed by Friedrich Hund, who was a German physicist, in 1927, and it was also noticed by two other people in 1927 whilst they were analysing the implications of a wave equation for the motion of a particle, and the main body of work took place throughout the 20th century. It's been used to produce tunnel diodes, which are types of p-n junctions whose current decreases as their voltage increases. Electric current in tunnel diodes are caused by tunneling, and they've been used in many things such as fast switching devices and computers. Here is my quote about quantum tunneling, and then there's my references.
Electron interference. The double-slit experiment was first performed by Thomas Young in 1801 using light. At the time, it was believed that light consisted of either waves or particles. However, with modern physics, we can now know that light could show both wave and particle behaviors. In 1927, Davison and Germer demonstrated that electrons show the same behavior. The double-slit experiment was later applied to electrons by Richard Feynman in 1965. When a beam of electrons passes through a single slit, it creates a single band. However, when passing through two slits, it creates an interference pattern like waves do, even though electrons are matter particles. On the left here, you can see the interference pattern created by the electrons going through two slits. When fired, the single electron leaves as a particle and becomes a wave of potentials and goes through the slit, interfering with itself and then hitting the wall like a particle. However, when scientists observed what slit it went through, the electron acted differently and no longer created this interference pattern, only creating two lines, as we can see here on the right. The observer collapsed the wave function just by observing it. In 1974, the Italian physicists Pier Giorgio Merli, Gianfranco Misaroli, and Giulio Pozzi repeated the experiment using single electrons and biprisms instead of slits, showing that each electron interferes with itself as predicted by quantum theory. Two quotes from Richard Feynman. Now we know how the electrons and light behave, but what can I call it? If I say they behave like particles, I give the wrong impression. Also, if I say they behave like waves. They behave in their own imitable way, which technically could be called a quantum mechanical way, a phenomenon which is impossible to explain in any classical way and which has in the heart of quantum mechanics. In reality, it contains the only mystery of quantum mechanics. These two quotes from Richard Feynman explain how bizarre the subject is. These are the four sources that I used, with the final one being a short film from Italy.
I'm doing my presentation on the ultraviolet catastrophe. So, in the late 1800s, Rayleigh and Jeans, who were two English scientists, came up with the theory that a black-body object would emit infinite amounts of energy as the wavelength moved towards zero. This can be seen as the dotted line in the diagram. When maths was first applied to this diagram, it predicted that the intensity would continue to increase as the wavelength decreased. This would mean that it would be emitting infinite amounts of UV radiation. This is not possible and doesn't agree with other areas of physics. The calculations did not anticipate in any way that the line would dip back down at the lower wavelengths. Classical physics, or to be specific, classical electromagnetism, could not account for the theory and/or the diagram. It was this mistake by Rayleigh and Jeans that led scientists to figure out that classical electromagnetism must be incomplete. In the early 1900s, Planck's law resolved the ultraviolet catastrophe. In simple terms, he discovered that energy released by objects is released in packets and must have a range of set values rather than a continuous range of any possible value. He introduced quantization, and this helped solve the ultraviolet catastrophe. However, Planck could not offer a good justification for his assumption of energy quantization. Scientists did not take the idea seriously until Einstein expressed a similar assumption to explain the photoelectric effect. Who and when? Rayleigh and Jeans were the discoverers of ultraviolet catastrophe in the late 1800s, but it was solved by Planck in the early 1900s. This is a quote given by Max Planck. And this is some of the websites I used.
Quantum entanglement. A summary of quantum entanglement. All fundamental particles have a property called spin, and when this spin is measured, the particle must either have spin up or spin down. Two particles are considered to be entangled when the spin of one particle is the opposite of that of the other. When one is spin up, the other is spin down, and vice versa. No matter how large the distance between these particles, when one particle's spin is measured, it is immediately known and a fact that the other particle has the opposite spin to this. If two entangled particles both have an unknown spin, both spins can be determined by measuring the spin of one of these particles. So in this diagram, we see two scenarios with two entangled electrons. So in the first scenario on the left, we see the first entangled electron has been measured to have spin up, so it's determined across any distance that its entangled electron partner has spin down. And in the second scenario, the first entangled electron has been measured to have spin down, so it's been determined that its electron entangled partner has spin up. The contradiction with classical physics. An entangled particle's spin is undefined until it is measured. All that is known is that the spin is opposite to its entangled partner. It is the moment that one particle's spin is measured that the other particle's spin is determined. And it appears that the first measurement of the spin of one of these particles immediately influences the spin of the other. These particles could be light years apart, suggesting that perhaps there has been a form of communication between these particles that is faster than the speed of light. If this were to be true, it would contradict the theory of relativity. Who is involved with the work? In 1935, quantum entanglement was discovered by Erwin Schrödinger and was later studied and developed by other scientists including Albert Einstein. Both Schrödinger and Einstein were displeased with the concept of quantum entanglement, as it appeared to contradict the theory of relativity. Einstein suggested that perhaps the entangled particles contain hidden information about their spin, therefore without the need for communication faster than the speed of light between these particles. However, in 1964, John Stuart Bell proved that there is no hidden information inside entangled particles using Bell's theorem. Practical applications of quantum entanglement. Quantum entanglement has applications in the technology of quantum computing and quantum cryptography. Quantum computing is the use of quantum mechanical phenomena to perform computation. Quantum cryptography, the science of exploiting quantum mechanical properties to perform cryptographic tasks. A quotation used for quantum entanglement. Albert Einstein described quantum entanglement as spooky action at a distance. And these are the websites that I used to do my research. Thank you for listening.
Welcome to my presentation on the de Broglie wavelength. The de Broglie wavelength theory is basically that everything in the universe can show wave-like properties depending on the experiment undergone. And the wavelength of matter particles can be shown using the same equation which is used for light particles. Wavelength equals Planck's constant over momentum, which can be seen here, and for the de Broglie wavelength can also be seen as Planck's constant over mass times velocity, as matter particles have mass and mass times velocity equals momentum. This theory was postulated by Louis de Broglie after other scientists conducted experiments with light in the early 20th century that showed confusing results. In the double slit experiment, which is the first one on the screen here, light diffracted once past the slits, which proved it was a wave. However, in the other experiment seen here, when light was shown onto a metal surface, electrons were ejected, which should prove particle behavior. This really did not make sense to scientists, and they just kind of accepted that light could be a wave and a particle, and they didn't really know why. So, because of this, de Broglie suggested in 1923 that maybe things we think are particles could show wave-like behavior also, and so have a wavelength that can be calculated through the same equation used for light. So other scientists, Davidson and Germer, conducted the double-slit experiment with electrons, and as can be seen here, sure enough, they showed wave behavior. So de Broglie was proven right, and he won a Nobel Prize. This theory does actually contradict with classical physics, though. In classical physics, particles and waves are considered different entities. However, the de Broglie wavelength theory synthesizes these two subjects. It turns out that they aren't that different. The most important use of this theory is in the construction of the electron microscope, which is used to measure objects of a very, very, very small size. De Broglie once said, "The electron can no longer be conceived as a single small granule of electricity. It must be associated with a wave, and this wave is no myth. Its wavelength can be measured and its interferences predicted." These are the websites I used. Thank you for listening.
The Compton Effect. Before, it was believed that photons only showed wave-like characteristics, but in 1923, Arthur Holly Compton proved that they had matter-like qualities as well, specifically energy and momentum. So, when photons, usually of the X-ray or gamma ray frequency, collided with loosely bound electrons, they would transfer some of their energy and momentum to them. The photons would then scatter at different angles, and these angles depended on the amount of energy they lost. And throughout the whole collision, energy and momentum are conserved because the electrons would have an increase in energy. The scattered photons would lose energy and therefore have longer wavelengths, so they'd be different. They are important nowadays to radiobiology, as this is the most likely interaction between high-energy electromagnetic waves and the human body. The quote was from Sir William Bragg: "The dividing line between the wave or particle nature of matter and radiation is the moment now. As this moment steadily advances through time, it coagulates a wavy future into a particle past." This, I think, means that the photons can go between matter-like qualities and wave-like qualities, depending on the situation. Evidence against classical theory. So it goes against classical physics, as light was thought to be a wave. So if it was believed that if photons were scattered off electrons, their momentum and energy would be the same. But Sir Arthur Holly Compton proved it wrong and showed that photons experience matter-like characteristics as well.
The photoelectric effect. The photoelectric effect is caused when photons hit a metal plate and emit electrons called photoelectrons. This process is called photoemission and is known as the photoelectric effect. This effect could not be explained with classical physics and experiments, but can be explained with quantum physics. What is the photoelectric effect? For example, the photoelectric effect works by high-energy radiation such as UV radiation striking the surface of a zinc plate. The high-energy photon has enough energy to eject an electron from the surface of the metal plate. If the photon does not have enough energy, then the electron stays in place. The higher the frequency of the radiation, the more energy each photon has to remove one electron from the surface of a metal, providing that the energy is higher than the work function of the metal. This is the equation used for the photoelectric effect, where Ek is kinetic energy, h is Planck's constant, and F is the frequency of the photon. Fo is the threshold frequency. HFO in advanced higher is known as the work function, as W, as HFO is equal to the minimum energy required to cause photo emission from a metal. W is given in joules. So this is shown graphically, where the x-intercept is Fo, the y-intercept is W, and the gradient is Planck's constant h. This diagram here shows the photons striking the metal surface and ejecting the electrons. The radiation has to have enough energy to remove the electrons from the surface, W. If the radiation does not have enough energy, then the electrons will not be removed. The red wave could represent visible light, as it removes no electrons from the surface. The red wave does not have enough energy due to its low frequency and long wavelength. The blue wave could represent UV radiation, as it removes a lot of electrons due to its high frequency and short wavelength. One photon removes one electron. The electron that has been ejected is now called a photoelectron. The diagram also demonstrates that the smaller the wavelength, the higher the frequency, which means more energy and therefore higher velocity the photoelectron has. So you can see this is here. In summary, the top wave has long wavelength, low frequency, low energy, and is less likely to emit photoelectrons from a metal plate. The bottom wave has short wavelength, high frequency, high energy, more likely to emit photoelectrons. So this is the history about photoelectric effect. Heinrich Rudolf Hertz first made the connection of light and electricity in 1887. Then another physicist, Philipp Lenard, confirmed this relationship. The experiment showed a light was shone at a cable cut in half. The electrons were transferring from one to the other. They could not explain why this was happening. Then they found out later that only certain lights worked at transferring electrons. We now know that high-frequency radiation is only capable of this, not normal light. This could not be explained with current understanding at the time, as they thought that light was a wave only. In the 1900s, Max Planck proposed an alternative explanation to the ultraviolet catastrophe. He suggested that energy can only be positive integer multiples of hf from the equation E = hf. This was then adapted by Albert Einstein in 1905, where he took the idea of positive integer multiples and combined it with one of his own hypotheses. In 1905, Einstein proposed that light is not a wave, but both a particle and a wave at the same time, which is now called wave-particle duality. He also suggested that energy is carried in packets called photons. The photons were neat positive integer multiples, which made sense with Planck's multiple of hf solution as well. This meant that radiation was quantized, as the energy that the source of radiation had was separated into photons, which are essentially particles. During this time, where Einstein's idea was introduced to an American physicist, Robert Milken. spent years trying to disprove the theory but ended up proving Einstein's theory right. He was quoted saying, "I spent 10 years of my life testing that 1905 equation of Einstein's, and contrary to all my expectations, I was compelled in 1915 to assert an unambiguous experimental verification in spite of its unreasonableness, since it seemed to violate everything that we knew about the interference of light." Einstein won the Nobel Prize for his work in 1921 for his work on quantum physics and mainly his discovery of the law of the photoelectric effect. And Milke was also awarded the Nobel Prize for Physics in 1923. This was a new way of thinking about light as a wave, and a particle opened a new branch of physics called quantum physics. This branch of physics was needed as it explains phenomena that we have seen previously but could not be explained with classical physics. Uses of photoelectric effect. The photoelectric effect can be used in solar cells and fiber optics. It can also be used to analyze the material by detecting the photoelectrons emitted. Originally, the photoelectric effect was used in simple phototubes, but now has been replaced with photodiodes that can detect light by letting the light through once it reaches a certain amount of energy, very similar to the work function. The photoelectric effect can also be demonstrated with an electroscope, as touching the top of the device with statically charged object will make the thin gold leaf rise. These are my sources. Thank you for listening.